So what we're looking at here is radioactive decay and the concept of half-lives. So whenever you have a radioactive substance, meaning something with an unstable nucleus, everything that is unstable seeks to be stable, which means the nucleus is going to try and emit protons, neutrons, or electrons in order to reach a stable state. While there's no way to predict this specifically, what we do have are what are called half-lives, where we know that over a specific period of time in the given substance, 50% of the parent isotope, 50% of its mass, will have emitted some of its mass and changed into a new daughter isotope. So, if we were looking at something like uranium, which we use to make nuclear warheads, produce nuclear energy, it has an extremely long half-life. But if we were looking at something like uranium-238, if we had 100 grams of this, after one half-life, we would be left with uranium-237 because we've lost one neutron from the parent isotope. Now, we're not going to go into all of that, but what matters is that in the span of one half-life, the parent isotope loses 50% of its mass, and that 50% is now a new daughter isotope. So, when we're looking here at our example, we see that we start with, at 0 half-lives, we have one parent isotope with 100,000 grams, and we have 0 grams of our daughter isotope. After one half-life, we're left with still 50,000 grams of the parent, but now we have 50,000 grams of the new daughter isotope, the new substance. Now, after 2 half-lives, this is once again cut in half. So now we go from 50,000 down to 25,000. So we're dividing by 2. Consequently, this side increases by 25,000 grams. And this happens over and over and over again until the parent isotope is essentially eliminated. This is something that you'll see when we create nuclear power. We have to take the leftover radioactive sludge, and because that has an extremely long half-life of tens of thousands of years, we have to go hide it somewhere essentially for years and years and years until it's at a stable enough level that it will no longer emit radiation and hurt people essentially. So, when we look over here on the next page at our example, we're looking at carbon-14. And carbon-14 is a substance that we actually use to help date a lot of artifacts and fossils that we find, because it's very, very exact in the rate at which it decays. So we can look at the carbon that's left over in something's body, say some old fossil from a dinosaur or a mastodon or something like that, and we can date it to a very specific time period because of the rate at which carbon-14 erodes. So what we see here is that one half-life for carbon-14 is 5,700 years, which sounds like a lot, but in the relative scheme of things, that's actually very, very short. So if we start with 10,000 grams of carbon-14, after one half-life, or 5,700 years, 50% of that carbon-14 has eroded now into a new substance, but we still have 5,000 grams left over. That's after one half-life. So, our second half-life, we're now 11,400 years in, and we should see 50% of this now having eroded to where we have 2,500 grams of carbon-14, and so on. So as our half-lives increase, every time the parent isotope, what's left over of it, should be going down by 50%. So you can see where if we were left, say, with 10 grams of carbon-14 from a living being, we could date that to approximately how many years old it is. So say it is 45,600 years old, roughly, because we can assume a constant rate of decay for carbon-14.